Okay, hello everyone. I am Siddhartha Pramanik, a PhD student from the Department of Mathematics, IIT Kharagpur. I will be the PMRF TA for this course, Computational Commutative Algebra. So, this is the first problem solving season, means the problem solving season for the first week. So, in this live session, I will be solving some problems based on the content of the first week. So now I will start by listing down the topics taught in the week 1. So the keywords for the week 1. So we started with the definition of ring. We saw some examples. Then we studied the ring homomorphisms. And then we saw the special type of ring, polynomial rings, which is the most important for us in this course. Next, we have saw different type of ideals. And how to create new ideal from known one, or operations on ideals. Like intersection, sum, uh, uh, product, colon, all those things. After that, we define a special type of ring known as Noetherian ring. And we have also saw some examples. Then we stated the Hilbert basis theorem. Then we talk about the proof that we will done it in a special case. So for that we first have proved the Dixon's lemma. Then we have talked about monomial ideals and monomial ordering. So monomial ideals and finally the monomial ordering. So as example, we talked about two monomial orderings, the lexicographic order and the graded lexicographic order. So in this live session, we will see one more example. So now let's start with some problems. So we have talked about polynomial rings, right? So let me write down. So okay, first I should mention that here I will write down that. So in this course, ring means commutative ring with unity, or at least in this live session. So ring means commutative ring with identity. Okay. And let me write down the first problem. So let R be a ring let R be a ring. So now from R we can construct one more ring, the polynomial ring in one variable with coefficients from R and in variable x. So this is the polynomial ring in one variable x whose coefficients coming from R. So this is a ring and R is sitting inside this ring. So we want to talk about some special type of elements of this polynomial ring. So let's see. Now let fx equals to a0 plus a1x plus dot dot an x power n belongs to Rx be a polynomial. Okay, so the first part says that, so when this polynomial means this element in this polynomial ring will be an invertible element. So fx is unit in Rx if and only if a0 is, a0 means the constant term of the polynomial, a0 is unit in R and the other coefficients a1 dot dot up to an are nilpotent elements of R. Elements of R. So this is the first statement, and second one is when we will say this fx is a nilpotent element in the polynomial ring. So fx is nilpotent in the polynomial ring Rx if and only if all the coefficients a0, a1 dot dot up to an are nilpotent element in the base ring. Nilpotent element base ring means R. So this gives the description of the nilpotent elements of the polynomial ring. And finally, we will talk about the zero divisors. So fx is a zero divisor in the polynomial ring Rx if and only if there exists some non-zero element, let's say 0 not equals to R in R such that R times fx is 0. So zero divisors means so fx is zero divisor, that means fx times gx should be 0, right, for some non-zero gx. But the third statement says that this gx we can take as a constant polynomial, means the element of the base ring. So let's see the proof of these three statements. So the first one, so what is the first one? So first one is about the invertible element of the polynomial ring. So fx is invertible if and only if the constant term is invertible and all other coefficients are nilpotent. So let's prove this. So first I will prove that so I will prove this reverse simplification. So for this assume that assume a0 is unit in R A0 is unit in R, and A1 dot dot AN are nilpotent elements sorry nilpotent elements in R. So using this, we need to prove that this polynomial fx is a unit. Okay, so now, since this a1 up to an are nilpotent, so we can say a1x a2x square dot dot up to an x power n are nilpotent elements. Right, because a1 is nilpotent, that will imply a1 power some m is 0. So if you take a1x whole power m, so that is basically a1 power m x, so it is 0. So same for the other elements. And since these elements are nilpotent, and we know that nilpotent elements forms an ideal, which we call as the nil radical. So consequently, their sum a1x plus a2x square plus dot dot plus an x power n is nilpotent. So this is because the set of all nilpotent elements forms an ideal. Elements forms an ideal, which is known as the nil radical. So A0 is a unit and this element is nilpotent. So what about the sum? So thus A0 plus this sum an x power n, which is basically the polynomial, is a unit in Rx. So this is because sum of a unit and a nilpotent element is again a unit. So this is a very basic exercise in a first course of ring theory. It's again a unit. So you should try to prove this one. If you are not able to prove, then you can write in the discussion forum. We will get back to you. So we have proved one side, that is if a0 is unit and other coefficients are nilpotent, then the polynomial itself is unit. Now let's prove the other way, which is the tricky part little bit. So if fx is unit, then constant term is unit and other coefficients are nilpotent. Okay, so for this, assume fx is unit. So for this, we will use induction. So we will use induction on the degree of the polynomial. Okay, so let's see how to do this. So the base step is when degree of fx is 0. So base step, degree of fx is 0. So that means fx is a constant polynomial. So fx is just a0. So this is an element of R, element of the base ring R. Now this is unit, so its inverse should be a constant element, right? So since a0 is unit, so sorry, since a0 is unit and all other coefficients are 0, so we have nothing to prove. So base step is done. Now assume the statement is true for all polynomials in Rx. Okay, so now assume, sorry, I should be more precise. So now the induction step. So let degree of fx equals to n, and assume the statement is true for all polynomials in Rx of degree less equals to n, sorry, n minus 1. So this is our induction hypothesis. So we need to prove the statement for fx. So now since fx is unit, so there exists some gx like b0 plus dot dot bm x power m such that their product should be 1, means the identity element. Now what is the product in terms of the coefficient? What is the leading term? Leading term will come from product of the leading term of g and the leading term of f. So that will give leading term is an times bm. Okay, so what we have to do is now compare the coefficients from both sides. So if we compare the coefficients from both sides, first we will get that the leading term is 0. So leading term is x power n plus m, whose coefficients is n plus bm. This is 0. So this is the coefficient of leading term. Now what about the second last coefficient? Second last coefficient will be an times bm minus 1 plus an minus 1 plus bm. This is also 0, right? So since in the right hand side only the constant term is surviving, so in the left hand side also only the constant term will survive. All other coefficients must be 0. So that is what we are writing. Now in this equation, sorry, this should be product. So if we multiply this equation with an, what we will get? So then we will get an square bm minus 1 plus an minus 1 an bm equals to 0. But this term is 0, right? So this will give you an square bm minus 1 equals to 0. So this is the second last coefficient. Second last degree coefficient. Now what about the third last degree coefficient? So how it is look like? an bm minus 2 plus an minus 1 bm minus 1 plus an minus 2 bm. So this is the coefficient of the term x power n plus m minus 2. So this is also 0. Right. Now let's multiply this with an square. So you will get an cube bm minus 2 plus an minus 1 an square bm minus 1 plus an minus 2 an square bm equals to 0. Now this term is also 0, this term is also 0. So what we are getting? An cube bm minus 2 is 0. So now continuing this, we will get an b0, where the power of an is m plus 1. This element will be 0. Now so this note that this product is 1. So this will imply a0 b0 is 1. So that means b0 is a unit. So here we will use that fact. So that will imply an power m plus 1 is 0, since b0 is unit. So this implies an is nilpotent. So we have found that the leading coefficient is nilpotent, right? So that will imply an x power n is also nilpotent. So then now let's see this polynomial gx equals to fx minus an x power n. Now fx is unit and this element is nilpotent. So sum of unit and nilpotent is again unit, is again a unit, and degree of gx is strictly less than degree of fx, because this is the leading term of f. So we are cancel out the leading term of f. So degree of gx must be strictly less than degree of f. So now we can use the induction hypothesis. So by the induction hypothesis, a1 up to an minus 1 all are nilpotent. So we have already found an is nilpotent. Now by induction hypothesis, other coefficients except the constant term is nilpotent. So we are done. So first part is clear, I think. So this one is clear. Now about the nilpotent element. Say polynomial is nilpotent if and only if all its coefficients are nilpotent. So let's see the proof of this. So first I will prove the reverse simplification. So let a0 up to an all are nilpotent. So then ai x power I is also nilpotent, right? That we have saw already, and this is for I equals to 1 to up to n. And since nilpotent elements forms an ideal, so their sum is also nilpotent. So their sum is a0 plus a1x plus an x power n. This is basically our polynomial fx is nilpotent. So this side is very easy. Now let's prove the forward implication. So let fx is nilpotent. So we have assumed that this polynomial is nilpotent, and we need to prove that all its coefficients are sorry okay. So we need to prove all its coefficients are nilpotent. So again we will use induction on the degree. Induction on the degree of the polynomial. So base step is degree of f is 0. So this is our base step. So in this case fx is just a0. So if this a0 is nilpotent, that is by just the assumption. So here we have nothing to prove. Now the induction step. The degree of f is equals to n. Now assume the result is true for all polynomials in Rx with degree less equals to n minus 1. So we need to prove it for the degree of f. So how to prove this? Now fx is nilpotent. So that will imply fx power some m equals to 0 for some m positive integer. Now what is the leading term of this polynomial? So leading term of this you will get that an power m. So it will look like n power m xn power n plus m and all lower degree terms. So leading term is just n power m. So just n power m is 0. So just an is nilpotent. Now again we will use the same trick. So that will imply an x power n is also nilpotent. So this will imply gx equals to fx minus an x power n is also nilpotent. Because fx is nilpotent, this element is nilpotent, and nilpotent elements forms an ideal, so their sum or difference is also nilpotent. And degree of gx is strictly less than degree of f. So by induction hypothesis, all the coefficients of gx which are a0 up to n minus 1, a0 up to an minus 1 are nilpotent. And we have already proved that an is nilpotent. So we are done. So we have proved we have given the description of invertible element as well as the description of the nilpotent element. The second, so the left part is the description of the zero divisors. So a polynomial is a zero divisor if and only if it is killed or annihilated by a non-zero scalar. That is what we have to prove. So one side is easy. So what about this side? So if there exists some non-zero element which kills f, then clearly fx is zero divisor because r is also an element of rx. So that side is trivial. So this, if there exists 0 not equals to r belongs to r such that r times fx is 0, then clearly fx is a zero divisor in rx. Okay, so we have to prove the other side, other implication. So for this, let fx is a zero divisor in rx. So we need to find a non-zero element r such that r times fx is 0. So again we will use induction on the degree. So we will use induction on the degree of the polynomials. So when degree of fx is 0, that is the base step. So then fx is equals to just a 0 and it is belongs to r is zero divisor. So then clearly the result holds, right? Because in r it is zero divisor means it will be killed by a non-zero element of r. Then clearly the result holds. Now let degree of f is equals to n and assume that the statement is true for all polynomials in Rx with degree less equals to n minus 1. So we need to prove the statement for fx which has degree n. So since fx is a zero divisor in Rx, so there exists a non-zero polynomial in Rx which kills fx, right? So there exists non-zero polynomial gx in Rx such that fx time gx is 0. Now let gx equals to b0 plus bm x power m. So then bm is non-zero because it is the leading term. Now let's put a name for this equation star. So from star we get an times bm is 0, right? Because the product is 0, so all the coefficients are 0 and this is the leading coefficient. Now if bm times fx is 0, then we are done, right? Because bm is an element of R and we have found a non-zero element. So assume bm times fx is non-zero. Now this bm times what is the degree of this bm times fx? So its leading coefficient is an bm, right, which is 0. So its degree should be less than, so degree of bm times fx, this polynomial is strictly less than degree of fx. And this bm times fx is a zero divisor because g times this element is 0, and bm fx is a zero divisor in Rx because bm fx times gx is 0. So by induction hypothesis, there exists non-zero R in R such that R times bm fx is 0. So we can take the element R times bm, which is a non-zero element in R. Okay, but how to prove that R times bm is 0? It is not clear, right? So to prove R times bm is 0. So we are inducting on the degree. So if we take mgx, mgx So what we have to do is, okay, so we have to do little bit. So here, since fx is a zero divisor, so we will get a non-zero polynomial which annihilates f, right? So we need to assume here something more. So let gx in Rx belongs to Rx a least degree polynomial such that gx times fx is 0. So here we are collecting the set uh, a belongs to Rx such that a times fx is 0. So this is clearly non-zero set. So in this set you collect a polynomial of least degree. Okay, so that is what we are assuming for G. So now fx times gx is 0, right? So uh, from this we can say uh, an bm is 0 because it's a leading coefficient, that we have already saw. So an gx is a polynomial which annihilates f. So okay, we need to be a little bit more precise. So now if degree of g is 0, that will imply gx belongs to R. So we are done. That is what we want to prove, that it is annihilated by an element of the ring. Now let degree of g is greater than 0. Okay. Now then an bm equals to 0, that will imply an times g gx is a polynomial of degree less than degree of g, right? Because its leading coefficient is n times bn, which is 0. So degree of n gx is less than degree of g, and n gx times fx equals to 0. So this polynomial also annihilates fx, but we have assumed gx is a least degree polynomial, and degree of this polynomial is also less than g. So this polynomial has to be 0. So this will imply n times gx is 0 because gx is of least degree which kills fx, which kills f of x. but this is a contradiction. So this will imply uh, degree of g has to be 0. So this will imply that gx belongs to R and it is non-zero. So gx times fx has to be 0. So we need to assume the minimality of the degree. Okay. So I have done the all three problems about the unit elements and important elements and the zero divisors. Now let's see a defined type of problem. So let f from q u v w, the polynomial ring over q in three variables, to q xy be a ring homomorphism defined by f of u equals to x square, f of v equals to xy, and f of w equals to y square. Then find the kernel of f. So this is problem from the practice problems given in the course page. So let's try to do it. So if you use Macaulay 2, so then you will get Macaulay 2, we will get kernel of f is the ideal generated by v square minus uw. Okay, so let's prove this by hand. Okay, now we will prove that this is the kernel. So now if we apply f to this element v square minus uw, so then you will get v is xy, so it is just x square y square, u means x square, w means y square, so this is 0. So that means v square minus uw is in fact in the kernel of f. So that will imply the ideal generated by v square minus uw is subset of the kernel. So one side is clear. So we need to prove the other containment. So for that, let p u v w be a polynomial in the kernel. Okay. Now we can thought this polynomial as a polynomial in V with coefficients from we can thought p u v w belongs to q u w. This is the base ring and polynomial ring over V. Just thought like this and then use the division algorithm. So now by the division algorithm we can write p u v w is equals to, so we will divide this polynomial by this polynomial v square minus uw. So then you will get q u v w times v square minus uw plus some r u v w, where either r equals to 0 or v degree, means degree of this polynomial r as a polynomial in this ring. V degree of r is less equals to v degree of this polynomial, and v degree of this polynomial is 2, is less than 2, right? So r is a linear polynomial of degree 1 as v degree. So we can write r u v w as some r1 u comma w times v plus r0 u comma w. So this is a degree 1 polynomial in v, right? Now observe that p is in the kernel that we have assumed, and this element is also in the kernel. So this minus this is in the kernel. Now since p u v w minus q u v w times v square minus uw belongs to kernel of f, so this will imply r u v w is in the kernel of f. So that will imply f of r u v w is equals to 0, but our r is this polynomial, and let's apply f on this. So if we apply f on this, image of u is x square, image of w is y square, v is xy. So let's put this. So it will be r1 x square comma y square times xy plus r0 x square y square equals to 0. Now observe that this is a polynomial in x and y. So what is the degree of x? So this contains all even degree terms of x, also even degree terms of y square, and we are multiplying x and y. So x degree is always odd, as well as y degree is always odd. So odd x degree and y degree, but in this term it has always even x degree and even y degree. So we cannot find any element between these two which will cancel out. So this an odd degree terms, this has even degree terms, so their sum is 0, so that will imply they has to be individually 0. So r1 x square y square times xy equals to 0, and r0 x square y square equals to 0. But this is variable, right? So we can say r1 is 0 as well as r0 is 0, but that will imply our r itself is 0. So what we are getting? So here our r is 0. That means this p is divided by this v square minus uw. So v square minus uw divides p u v w. So that will imply p u v w belongs to the ideal generated by v square minus uw. So our kernel is equal to the ideal generated by v square minus uw. So this is just mimicking the proof which we have done in the lectures. We have done one example in the lectures, just mimic the proof. I hope you will solve this type of questions in the assignment. So please do solve that. So this is the second question. Now let's move on to another problem. So question number 3. So let phi from R to S be a ring homomorphism and I an R ideal and J an S ideal. So this exercise is about extension and contraction of ideals. So recall that here you have R, here you have S, here you have phi, and you have the ideal I. Now if you extend it, the extension is the ideal generated by, we denote it just IS, but it is actually ideal generated by the image. And if you take an ideal J in S, if you take the contraction, we denote it by J intersection R, but this is the set R belongs to R such that phi of R belongs to J. So these are the definition. This is the extension of I in S via phi. This is the contraction of J in R via phi. So the problem is, if you take I, then it is subset of the extension of I and then contract it back. So first you extend to S and then again contract it back. And the second problem is, so if you take J and if you contract it and again if you extend it, then it will contain the original ideal J. Okay, and these are containments. We will also give okay, let me write it here. Give examples to show that the above inclusions can be strict. So that means we can give examples so that this equality may not hold. They can be proper subset. Okay, so first two parts are very easy. So let's solve this. So first part. So we need to prove I is subset of its extension and again contract it back. So let's A belongs to I. So that will imply phi of A belongs to its extension. Now that will imply that A belongs to its extension and again contract it back, because by the definition it is the set of all those elements whose image is in J. So it is clear that I subset of IS intersection R. Now the second part. So if we take contraction and then again if we extend it, it will contain J. So let's take an element from J. Oh sorry, it should be the other way. This one. So let Y belongs to the extension of J intersection R, extension of contraction. So how this element looks like? Now this ideal is basically uh, ideal generated by phi of j intersection r, right? So this is just by this definition. So our y must be look like uh, some ai times yi, I equals to 1 to n, where ai belongs to s and yi belongs to phi of j intersection r. So then again we can write it as ai times phi of xi, I equals to 1 to n, where uh, phi of xi is equals to yi, because yi are in the image, so we can write it like this. But uh, yi is in the j intersection r, so xi must belongs to j intersection r, right? Okay, so let me write it here. Since yi belongs to phi of j intersection r, this will imply xi belongs to j intersection r. So this will imply phi of xi is in the j. So if this element is in j, its linear combination is also in j. So this will imply y equals to summation ai phi of xi is in j. So we have taken y from this ideal and y belongs to this ideal. So j intersection r and extend it to s is subset of j. So part B is also clear. Okay, now the examples. So we need to give example so that this is a proper containment. So let I from Z to Q be the inclusion map, be defined as I of n equals to n for all n. Then it is clearly a ring homomorphism. Then if you take I equals to 2z, then what is okay, here we are taking z to q, here you are taking 2z, so what is its extension? So here the image is itself 2z, so I q is actually the ideal generated by I of I, and which is itself I, which is generated by 2z, but in q all non-zero elements are unit, so this should be q itself. So extension of I is q itself. Now if you contract it back, iq intersection z means the so here you are taking q and you are contract it back, means you are taking the inverse image. So this is basically z, right? So here I is 2z, which is proper subset of iq intersection z, which is Z. So this is first example. Now second example, which is from, I will take from the practice problems itself. So let phi from Z to Zx and take the ideal J as ideal generated by x plus 1. Then what is J intersection Z? What is the inverse image of the elements of J under phi? This is just inclusion map. N goes to N. So this will be basically 0 because elements, because J has no elements of Z. So that will imply, now if you take its extension in Zx, so extension of 0 ideal means the ideal generated by 0, which is basically 0. So it proves that J intersection Z, and again if you extend it, it is proper subset of J because it is 0 and it is ideal generated by x plus 1. So let's see what we have done so far. So rings and examples we have saw. From homomorphism we have done the kernel problem. Polynomial ring we have saw some properties, and dependent of ideals means we have saw operations of ideals. Okay, now Noetherian ring and examples. Okay, let's see some non-examples of Noetherian rings. So this is problem number 4. Is it 4? Okay. So problem number 4. So prove that the ring R equals to K, what was the ring? K, okay, Kx, comma xy, comma xy square, xyq dot 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 so on, subset of the ring Kx comma y is non-Noetherian. Okay, so we have to prove that this ring is non-Noetherian. So we have saw 3 equivalent conditions for a ring to be Noetherian. So we can use any one of them to prove the counterpart. So to prove non-Noetherian, okay, let me write. To prove R is non-Noetherian, we will show there exists an ascending chain of ideals which does not stabilize. So from this we can guess one ascending chain of ideals. So we will show that this ideal generated by x, proper subset of ideal generated by x comma xy, proper subset of ideal generated by x comma xy square, and so on, is an ascending chain which does not stabilize. So it is an ascending chain, it is clear, but we need to prove that it does not stabilize. So claim, so it does not stabilize means this strict inequality will occur in every place. We will not get equality in any place. So we will claim that, so we can show that this equality will not hold, means these two ideals will not be equal. Claim that x comma xy dot dot x comma xy power n plus 1 will not be equal to x comma xy power n. So which is equivalent to xy power n plus 1 does not belongs to the ideal x comma xy power n. So we need to prove this fact. So this I will prove this by contradiction. So suppose xy power n plus 1 belongs to this ideal xy power n. Then what we can do, we can write this monomial as summation gi times x y power I, where I is equals to 0 to n, and this gi is an element of the ring R. So it is in this ideal, means we can write this as linear combination of these generators. Okay, so now observe that in the left hand side, here x degree is 1 and y degree is n plus 1, but here just in this monomial, here x degree 1, y degree is I, and I is less equals to n. So to get the equality, y degree must be n plus 1 for some gi times. Okay, let me write. So this will imply y degree of some polynomial, let's say gi x power I is n plus 1. So for this, one y should be come from this gi, right? So that will imply degree of some gi. So that will imply so what is gi? Gi is actually polynomial in R, right? That means gi is a polynomial of x, xy, xy square up to xy power some m. So it must contain some element which involves y. So gi must have some non-zero term as x power xy, right? Then it will give the total degree is n plus 1. Okay, some xy power j, so that y degree of gi xy power I equals to n plus 1. But in that case, it involves one more x also. So in that case, x degree of gi x y power I is, so here you will getting one more x, and here you have one x, so it is 2. But in the left hand side, your x degree is 1, but in LHS x degree is 1. So this is a contradiction. Hence xy power n plus 1 cannot belongs to this ideal x comma y dot x power y power n. So this chain will never terminate, it will never stabilize. So this ring is non-Noetherian. Hence R is non-Noetherian. So we have given an example of non-Noetherian ring. Now this example, from this example we can conclude some more things, right? So what is that? So I will put those things as remark. So remark number 1. So observe that I have written that R is a subset of kxy, because it's obvious, it's a subset of kxy. But from Hilbert basis theorem we know that this is a Noetherian. But here R is a subring of kxy, but R is not Noetherian. So first remark is subring of a Noetherian ring may not be Noetherian. Okay, but okay, so in fact we can say something more. So this thing is a K algebra. I hope K algebra was introduced, and this is also an K algebra, and this is Noetherian K algebra. So sub algebra of a Noetherian algebra need not be Noetherian. That it can also say. Sub algebra of a Noetherian algebra need not be Noetherian. Okay, so this is one important example. So I want to mention that using this example, one can produce some more counter examples in future problems, which will appear in the courses. So you should observe those things. Okay, that's all. Okay, let's move on to another problem. Okay, so we have talked about the Hilbert basis theorem, right? So what Hilbert basis theorem says is, so I will write down the most general statement of Hilbert basis theorem, because in the course it is just a particular version to do the computational aspects. So it says that R is Noetherian ring, it will imply the polynomial ring in one variable is also Noetherian. Right? So this is the usual statement of Hilbert basis theorem. So what about the converse? So if we assume Rx is Noetherian, can we say that R is Noetherian? So the answer is yes. So if Rx is Noetherian ring, so any homomorphic image of Rx or any quotient of Rx is Noetherian. So that will imply if you take the quotient of Rx by the ideal generated by X, this is Noetherian. But what is this? This is isomorphic to R. So R is Noetherian. So converse part is very easy. So converse of Hilbert basis theorem is true. So one should know this. Okay. So maybe I will do one more example of non-Noetherian ring. Okay, it's problem number 6. So prove that uh, prove that the ring, let's say R equals to K x comma y, x by y, x by y square dot dot so on, and it is subset of the fraction field of kxy, is a non-Noetherian ring. So again, to prove that this ring is non-Noetherian, we will adopt the earlier method. So what we will do is we will find a ascending chain of ideals which does not stabilize. So observe that if you take the ideal generated by x, it is contained in ideal generated by x by y, because if you x by y multiply with y, it will give you x, and this is contained in ideal generated by x by y square, again the same reason. Is an ascending chain of ideals. So we need to prove that this chain does not terminate. So we will prove that all stage we have proper subsets. So claim x by y power n is a proper subset of x by y power n plus 1 for all n greater equals to 1. So this chain, so our claim is this chain never stabilizes. So we will prove this by contradiction. So suppose equality holds, x by y power n is equals to x by y power n plus 1. So that will imply x by y power n plus 1 will belong to this ideal x by y power n. So that will imply x by y power n plus 1 equals to some f times x by y power n, where f belongs to the ring R. Now we will multiply by y power n plus 1 both sides. Then we will get x equals to f times x y. Now easily see that here it does not involve any y, but it involves y, right? So so we need some 1 by y, so that should come from this f. Since the LHS has no y, so for the equality f must have some term involving 1 by y. So f is a polynomial whose variables are this. So let me write it here. So f is actually polynomial in this x by y dot x by y power some m. This is belongs to R. Because a polynomial involves only finitely many variables, we are taking just m. So it must involve some term which involves 1 by y. But the only variables which involves 1 by y also involves x. But then the term which involves 1 by y also involves x. So this will give the x degree of the right hand side is 2, but here x degree is 1, which is a contradiction. So that means this equality cannot hold. Thus, we have found an ascending chain of ideals in R, which never stabilizes. Hence, R is non-Noetherian. So this completes the proof. So if you are not able to understand this, you may write in the discussion forum and we will come back to you accordingly. Okay, this is problem number 6. Okay, let's move on to another part, monomial ordering. So I should do one more example, monomial ordering, which is the graded reverse lexicographic order. So this is graded reverse lexicographic order. So how it is defined? So you take one polynomial. So recall that our ring is k x1 x2 up to xn. Now take two monomial x1 power a1 dot dot xn power an, and another one is x1 power b1 dot dot xn power bn. So we say this monomial is greater than this, and we denote as G Reblex. So we say this monomial x1 power a1 dot dot xn power an is greater than x1 power b1 dot dot xn power bn in G Reblex if the total degree of the left hand side is greater than the total degree of the right hand side, or the right most entry in this difference of the vector a1 up to an minus b1 up to bn rightmost entry in this vector is negative. So this is the graded reverse lexicographic order. So either the total degree is bigger or the rightmost entry in the difference vector is negative. So let's see some examples to digest this definition. So you take R as the polynomial ring in 3 variable. Okay. Now if you take xz and y. So let's compare this with the other two definitions. So one is just lex or lexicographic. This is the first example we have saw in the lectures. The second is glex, graded lexicographic, and the third we have just saw now, graded reverse lexicographic, G-Reblex. So what lex is saying is, you see the left, so this saying is leftmost entry should be positive. Leftmost entry in a1 dot dot an minus b. Okay, I am writing too much small. So leftmost entry in the difference vector must be positive, and glex is either total degree is bigger or it should be bigger in lex, means the leftmost entry in the difference vector is positive, and G-Reblex is either the total degree is positive or the rightmost entry is negative. Rightmost non-zero entry, sorry, I should be precise. Rightmost non-zero. Here also the leftmost non-zero entry. Okay, so let's compare this lex in lex. What about in lex? So what is the vector? So okay, let me write it very clearly. compare this and this. So for this the vector is 1 0 1, and for this the vector is 0 1. Okay, let me take y square. So the vector is 0 2 0. So you can see the total degree is same, but for legs we need to see the leftmost entry, so you need to check the difference. So this is 1 minus 2 1. So the leftmost entry is positive, so in legs it is bigger. Now what is in G legs, graded lexicographic order? Since the total degree is same, it has also total degree 2, it has also total degree 2, we need to check in legs. So legs is this first one is positive, first one is bigger, so in G legs it is the same. But what about G rev legs? So total degree is same, so we need to check the rightmost non-zero entry. So rightmost non-zero entry, this minus this is positive, so 0 2 0 minus 1 0 1. In this case the rightmost entry is 1 2 minus 1. In this case it is negative, so this must be the bigger. So we have the other thing for the G rev legs. So y square is G rev legs bigger than xz in G rev legs. So I hope it is clear. So let me write it here, because 0 2 0 minus 1 0 1, and this is basically minus 1 2 minus 1. So the rightmost entry is negative. Okay, so I think I have covered almost all the topics in the week 1. So I think it is better to stop now, and we will meet in the next week.